Welcome to a video on KRC low-pass filter designs. Okay, in this video we will look at second-order filters and then higher-order filters using these second-order stages. So first we will look at the KRC filter as is before we do the cascading. So we will look at the circuit, the equations, the choices that we can make, and some tweaks. Then we will do some designing from a filter table, do some design problems, and look at the simulations of these design problems. Okay, so second order filters has a Q factor. Okay, so this is for the low pass and the high pass filter, and basically the Q factor is a bit of a instability or a resonance that you can have in your second order filters. They have a bit of positive feedback, but having this we can have a very sharp roll off available. Okay, so all of our KRC filters, we have a design frequency and we have a design Q factor for both low pass and high pass. Right. Now, the KRC low pass filter configuration is of order 2. So the resistors and capacitors on this side of this figure is mainly responsible for the cutoff frequency, and RA and RB here is responsible for the Q factor. Okay, so the passband gain of this filter is 1 plus RB over RA. So the two resistors responsible for the Q factor also gives the final gain of the amplifier. Right. The cutoff frequency is dependent on only these capacitors and resistors right here, and the Q factor is dependent on everything. Okay, but this is kind of complicated. So let's look at some ways to make life easier for ourselves. And there is two methods to design one of these filters. One of them is equal component design, which is the obvious and more typical choice, and that is to choose the resistors to be the same and the capacitors to be the same, and the frequency reduces to 2 pi 1 over 2 pi RC. The Q factor reduces to 1 over 3 minus K, where K is the ratio of RB and RA plus 1. Note that K should always be smaller than 3. Okay, the moment that the K becomes larger than 3, we build an oscillator. Plain and simple. Okay, so this gain will always be less than 3. That is the first design criteria or design method. So you have 3 equations for your design. The second one is a unity gain design. So in the passband you will have 0 dBs, so K is 1 volt per volt. This is also the minimum component approach, so the filter, the op-amp just becomes a buffer circuit. Right? And your Q is the ratio of components. So if you set R2 equals to R, R1 becomes M times R. Same with a capacitor, and N times the capacitor. So the ratio of a components will make up your Q factor, and it will make up your cutoff frequency. Here every component will have a different value, and you have to choose your M and M so that you have components that is really close to the ratios that you have chosen. So the typical method here is to choose n equal to 1. So then you can choose your two capacitors to be the same value, and then your Q factor is more dependent on the ratio of resistor 1 and resistor 2. Okay, or you can pick the resistors to be the same value, and then it becomes dependent on your capacitor values. Right, so that's a unity gain design. Unity gain design also maximizes the bandwidth that is available for a op-amp. Okay, we will mostly look at the first approach. Right, so designing from a table, we're going to use cascaded design using normalized values from a table. So if you're building an odd order, then it's going to be a bunch of second orders plus a first order filter, and you can just sum the orders to get the final order value. And in an odd order, you can use the first order filter for your gain correction. If your order is an even number, you can just use KRC after KRC section. But if you have a different final gain in mind, you need an extra gain correction stage. No messing with RB and RA to try and fix your gain. You will build the oscillator if you do this, or mess up your Q factors, and your filter will not respond like you intended to. Right. From the tables, if you're designing a low pass filter, you take the cutoff frequency that you're designing for, multiply it by the value you get from the table, and that is the design frequency that you're going to use in this equation right here. You also get the Q factor from the table, and that will give you resistor B and resistor A's values. For a high pass filter design, you're just going to take the cutoff frequency that you're designing for and divide it by the table value. This ensures that it flips from a low pass filter to a high pass filter design immediately. So, the best way to do this is to go through some problems. So the first problem is, let's design a third order Butterworth filter for a 10 kHz cutoff frequency and a final gain of 20 decibels. Let's use 1 nanofarad capacitors in our design and equal components throughout. So R1 and R2 should be the same, C1 and C2 should be the same, RA and RB will be quite different. So we must calculate all the required components and select E192 resistors for the best accuracy. So better resistors, better filters. And lastly, we will simulate the problem and have a look. Right. So third order, 10 kHz, 20 decibels. Right. Third order means one KRC section and one first order filter like this. Okay, so 2 plus 1 is 3. So we will design this in stages. So we will design the KRC and then the first order filter together with the gain correction. So since this should be Butterworth and third order, let's go to the table. So third order right here, and F01 is 1, Q1 is 1, and F02 is 1. So this is the KRC section, and this is the first order filter that we must design. So for the KRC stage, N is 2, so the frequency that we're designing for is the table value multiplied by the cutoff frequency that we want. Let's choose all the capacitors with same value at 1 nanofarad, and we must then calculate the resistors R1 and R2, equal components, let's call that R. So solving for R, we get 15.915 kilo ohms, and the closest value is 16 kilo ohms. The Q factor goes into our equation, and we can find the gain that is required. So 3 minus 1 over 1 is 2 volts per volts. So if RA and RB has the same value, K would be equal to 2. So let's just choose them both 1 kilo ohms. Right, and that is the first stage completed. The second stage is the first order. So FC2 is the table value multiplied by the cutoff, again 10 kilohertz. This is why the Butterworth is component saving. Okay, you don't have too many component values, and it will turn out to be the same 16 kilo ohms. I typed this in wrongly. This should be 15.9, the same as right here, 915. Okay, sorry, my bad. Dyslexia took over a bit. Anyways, so this will be 16 kilo ohms. So the same as the first stage. That is the very nice thing of the Butterworth. You can design one and everything will be the same. The only thing that will differ from stage to stage is RA and RB. Right. Our final design gain is 20 decibels, and that's 10 volts per volts. 20 decibels, yeah. Okay. So all the gains multiplied will be this KT value. So KT divided by K1 would be the value of the second stage, and that's 5 volts per volts. Use 1 plus R5 over R4, and 4 kilo ohms would be required to do this. So let me jump into our simulation and check how our filter responds. Right, so I've built our design in LT-Spice, and let's do the baud plot from 1 Hz to 1 megahertz. And you can see that we have our 20 decibels that we designed for. Switch off this phase plot, and we have a nice sharp cutoff right here. And in 1 decade, this is third order, we should have 60 decibels cutoff. So from 20 to minus 40 in 1 decade, from 10 kilohertz, we have our cutoff rate. So that is 60 dBs, and 20 to 17. Let's see. 17, and we're at 9.89 kilohertz for our cutoff. Okay, if we try to get this closer, 9.962 kilohertz. So this is really close to what we actually designed for. Okay, and there is our third order Butterworth filter designed and simulated. Right, let's look at another problem. So the next problem is a fourth order 0.1 dB Chebyshev low pass filter. Let's go again with a 10 kilohertz and the 20 dB final gain. 1 nanofarad capacitors. Same old, same old. So fourth order 10 kilohertz, 0.1 dB Chebyshev, 20 dBs. Those are our requirements. Fourth order means we will cut off at minus 80 dBs per decade in the end. Right. So, second order KRC, second order KRC. These are 4 orders. We're going to have to do gain correction in the end. So just a normal non-inverting amplifier is required. nothing in between here. Right, so from the table, fourth order, so for our first KRC stage, F01 is 1.153, and we have a high Q factor of 2.183. Second, smaller frequency, lower Q factor. Right, so these are the values that we're going to use in the first stage and this in the second stage design. So for the first stage, we take our design frequency and we multiply it with a table value and we get 11.53 kilohertz. Choose our capacitors at 1 nanofarads, our resistors to be the same, and we get 13.8 kilo ohms for our first stage. We calculate the gain using the Q factor, and the gain is 2.5419 volts per volts. Using our RB and RA values, we can build this gain. So choosing RA as 1 kilo ohms, RB would just be 1.5419 kilo ohms. So just subtract 1 from this. And the closest E192 is 1.54 kilo ohms. That is the design of the first stage. Second stage, multiplied by 0.789, and you get 7.89 kilohertz, and that amounts to a 20.17 kilo ohm resistor, and we need to pick a 20.3, which is the closest, and this is a very large difference, and that will mess around with our the ripple that we see. I'll show you in the simulation. Right, here we're also using the lower Q factor, and our gain reduces to 1.384 volts per volt, and with a selection of a 1 kilo ohm resistor, we get 383 ohm resistor here for RB. Right, that is the second stage. So for the gain correction, we get 2.5419, 1.3845, and both of those are going into our gain correction stage. We want 20 decibels, which is 10 volts per volts. Take our 10 volts per volts, divide it by the first two stages gain, which is multiplied, and we get a 2.8415 volts per volt gain for our gain correction. Calculate the resistors. 1K and 1.84 kilo ohms will fix our gain to 20 decibels final gain. So let's jump over to the simulation. So here is our simulation doing 1 hertz to 1 meg. Let's run it. Let's look at this output. You can see that there is a very sharp cut off. And from 20 decibels to minus 60, so that is 4 decades, and we are fairly close right here, so minus 80 dBs per decade. If we zoom over this area right here, you can see the ripples. They are not as smooth as the one in the other table, but this is very close to a 0.1 dB ripple right here. Okay, and if we take our cursor, let's go find our minus 3 dB point. This sits a bit further away at 12.07 kilohertz. That is due to our component choices that was not as accurate, but this maximizes the pass band so that we have our 10 kilohertz in the pass band right here. So if we zoom in, it is very close to this point before we have that very sharp cut off or brick wall approximation. And 0.1 dB ripple is not that bad. So this is actually a very good filter in general with a fast cutoff rate and maximization of the passband. Lastly, I have another simulation where I am comparing the two. So if we run it, we can see the very fast cutoff rate of our Chebyshev here. This is a third order, this is a fourth order. So we can see the different cutoff rates as well. And if we zoom in, we can see the maximization of a passband for the Chebyshev and the Butterworth right here. There's our ripple, and due to the component choices, a little bit of a difference in the passband, but it looks kind of nice. Okay, that is low pass filter designs from tables. Thank you for watching and see you in the next video for the high pass filter design.